So we are in chapter 11, two sample tests of hypothesis. In this chapter, we would like to be able to compare two populations with respect to some characteristic. That would be the random variable, the characteristic. So the question might be, how are we going to compare these two populations? Perhaps the best way to compare two populations is through comparison of their respective population means. So for example, if you want to know which brand is favored, we have two brands, brand A, brand B, and you want to know which brand is favored over the other one, we may create an index and then look at the average score on that index for brand A versus brand B, and then by comparing those indices we can decide which brand is a better brand. So that is why a lot of times the comparisons are done through averages. So for us, the averages are going to be mu1 and mu2. So remember, mu is the population mean. The subscript 1 means the first population mean. Mu subscript 2 means the second population mean. So that is what we're going to compare. Now we will compare these two population means by looking at actually the difference between them. That's what we're going to look at. So again, in order to be able to compare two population means, we're going to look at the difference between their means. And the reason for doing that is I have it in highlights here. Because if we compare two population averages through the differences, a difference of 0 would indicate that there is no difference between the two means, right, between the two averages. And if the difference, let's say we have mu1 minus mu2 is less than 0, a difference of negative would imply that mu1 is higher than mu2. So, or actually, I'm sorry, mu1 would be less than mu2 in this case. If a difference is greater than 0, that would imply the average in the first population exceeds the average in the second population, or it's greater than that. And then we can interpret each of these in respective contexts. So for example, if the average speed for male is less than the average speed for females, that would lead into if it's less than, so mu1 would be the average speed for male, mu2 average speed for females. If that difference is less than 0, that would mean female drivers drive faster than male drivers. Now, in order to be able to do our inferences, we need to find point estimates of mu1 and mu2, and the best point estimates for mu1 and mu2 are going to be the respective samples. So for mu1, the first sample mean, for mu2, the second sample mean, are going to be our best estimates, point estimates, that is. Now, when it comes to comparing two means, we're going to look at two scenarios. The first scenario is where we have two independent samples. And then the second one would be where we remove that assumption and we assume the samples are matched, paired, or they are dependent samples. Okay, all of those mean the same thing. So let's take a look at a case where we have two independent samples. So first, population standard deviations are unknown and they are different. And second, we're going to look at a case where population standard deviations are unknown but assumed to be equal. Now both of these numbers 1 and 2 fit under the independent sample categories. Okay, so again, we have two situations where we have independent versus dependent samples, and within independent samples we have two cases here. The population deviations are either equal or they are different. In both cases they're unknown. So here what I've done is I've drawn a conceptual drawing of how things are shaping up. The two normal distributions that you're looking at, these are, let's say, the parent distribution, or the distribution of the parent population, I should say. So I have, let's say, same random variable that I'm comparing in the two populations. So we're going to assume normality of both populations. So the center of the first population for this random variable x1 is located at mu1, the center of the second population mu2. Each of these have their own standard deviation. Again, in one instance they will be different, another instance they would be assumed equal. So these are, remember, these are the distributions of individual scores. So for example, if I'm interested in comparing the FICO score of again, male versus female, let's say. So the population that on the left is this one. This is going to be the distribution of FICO scores. Let's say for all females, there's going to be tens of millions of those here. And the distribution to the right would be individual FICO scores for male. And again, you have tens of millions of scores here. So what do? We go and we obtain individual samples, right? Now, although in practice we only get one sample from each population, but theoretically, in order to arrive at the sampling distribution, we're going to assume we're going to take repeated samples of size n1 from this population, repeated samples of size n2 from the second population. And then by central limit theorem, remember, the sampling distribution of x bar is going to be normal also with the same center. And deviation, of course, sigma of x bar 1, which we showed it was sigma over root n. And the second population likewise. So now we moved from random variable x to random variable x bar. And then because we're looking at the difference between the two population means, we're going to join these two distributions through x bar 1 minus x bar 2. Now, it turns out that because x bar 1, the sampling distribution or probability distribution of x bar 1 is normal, and probability distribution of x bar 2 is also normal, that any linear combination of x bar 1 and x bar 2 would also be normally distributed. Okay, so the difference between the sample means, it's going to be normal. The center is going to be mu of this random variable, and that's deviation of this random variable. Now, a few cryptic notes here. Mu1. So let me go back up here. Remember, this is the mean of the first population, mean of the second population. These two means up here are what we really want to compare. That's what we're after. We want to compare these two means. So how are we going to compare them? Because of the way we have designed the experiment, we're going to look at this mean. That's how we're going to compare those two means. So mu1 equal mu x bar 1. What we're saying is that this mean is equal to this one. And the second mean of individual scores is equal to the mean of the sample means for the second population. These are equal. These means are equal. There. So if I want to find the average of x bar 1 minus x bar 2, we just simply subtract the mean of x bar 1 minus the mean of x bar 2. But because of this relationship, that turns out to be mu1 minus mu2. See, this is what we wanted to do. So we're going to do this through this distribution. And x bar 1 minus x bar 2 is going to be our statistic. Okay, so let's talk about now the sampling distribution of x bar 1 minus x bar 2. Remember, x bar 1 minus x bar 2, these are the sample statistics. So that's going to be a point estimate of our population, mu1 minus mu2. Now the sampling distribution is normal, as you can see up here. If we sample from normal populations, and it's going to be approximately normal otherwise, provided each sample size is at least 30. So, because the distribution is normal, it has its parameters, its mean, and its deviation. And these are the formulas for the mean and deviation of those. Okay, we are not going to work directly with these. Okay, remember we use Megastat in this course, so that's going to be our source of analysis. But this is good to know. These are the parameters again of that normal distribution. This one. Okay. Now, Just a reminder here again, a point estimate of the difference in the population mean is the sample means. Okay, now the standard deviation is also estimated here. This is what the theory tells us is going to happen. But since we don't know the deviations, we're going to use the sample standard deviations, right? So how we estimate them actually depends on our assumption, whether the two deviations are equal and unknown or different and unknown. Now the formulas for these are in the book again, but I'm not going to go over them since we're going to use megastat. Now, and as always, once we have the probability distribution of a statistic, its sampling distribution, then we can make probability statements about that statistic, and we can further go and construct confidence intervals and test hypotheses about the parameters of the population. So it's a good thing that we know that the sampling distribution for x bar 1 minus x bar 2. Now, let's take a look at an example of how this is going to work. Okay, so this example is from your book. This is the example for two sample pool t-test. That's what we're doing. So we're doing two independent samples, and our procedure is known as a pool t-test. The word pool here means averaged. Pooling is a way of averaging two quantities. So that's our procedure. So this is for equal but unknown population deviations. Remember, equal but unknown. The key word here is equal. So sigma 1 equals sigma 2. Let's read on. In this example, we have a recent study compared the time spent together by single and dual earner couples. According to the records kept by the wives during the study, the mean amount of time spent together watching television among the single earner couples was 61 minutes, a little over an hour a day. So this is again for single earner couples. So for example, only the husband works or only the wife works. So I guess that would mean they have more time to spend together doing something, with a standard deviation of 15.5 minutes. Now for dual earner couples, this is where both couples work. The mean number of minutes spent watching television was 48.4 minutes, almost 50 minutes, so about 10-11 minutes less, with a deviation of 18 minutes. At 0.01 significance level, that is our alpha, can we conclude the single earner couples, on average, spend more time watching television together. There were 15 single earner and 12 dual earner couples studied. So again, from the onset, if you look at this, 61 minutes, let's call it an hour, versus 50 minutes. The difference, clearly, there's at least 10 minutes difference between them based on these small samples, and that's not good. We don't like small samples, but it is what it is. So the question is that difference of almost 10-11 minutes, is this statistically significant, or is that just by sampling variation? It's noise, that's what it is. So what we're going to do is we are actually going to run this in megastat. Okay, so what I've done here is I've actually determined the parameters of the two populations here, so we know exactly what it is that we are trying to estimate. So I'm going to let mu1 be the average time in minutes spent together watching television among all single earner couples. Okay, notice how inferential this is. This is for all of them. You see that? It's not just for the sample. Mean is a population mean, so this has to be for all single earner couples. So if I'm a single earner couple, let's say, this would pertain to me. I'm going to let mu2 be the average time spent together watching television among all dual earners. Okay, that's what those are. So the question here that's asking is, on average, single earner couples spend more time on average, more. So the way I've defined this, that means mu1 is greater than mu2. Mu1, remember, average time spent by single earners exceeds that of the dual earners. The null, we always take it to be equal, always. So the null says there's no difference between them. That single dual earner has nothing to do with it. Okay, so that's what that is. Okay, and so that's what the null hypothesis is. Now, what's given here I have actually written down. Okay, so we have n1 is 15, n2 12. I got those directly from the statement of the problem. Okay, so the first sample mean is 61 minutes. Remember that one? X bar 2 was 48.4 minutes. The standard deviation for the first sample is 15.5, and the standard deviation for the second sample is 18.1. Now remember, if we assume the population deviations are equal, these two numbers, 15.5 and 18.1, should really have been the same, huh? Because that was our assumption, that these are the same in the population. But we know in the samples, these are most likely are not going to be the same. So the question is, if they're equal, and we want to go about it in that direction, how can I make which one, if you will? Which of these should I use? They're supposed to be equal. Should I use 15.5? Should I use 18.1? Should I just average them maybe, or what shall we do? Well, the process is called pooling them again. What the pool deviation does, pooling these two deviation, it actually averages them, but it also takes into account the sample sizes. Okay, so let me show you the output from Megastat, and then I'll go actually and do this click by click, step by step in Megastat. But once we go to Megastat and run it, this is what it's going to look like. The procedure is hypothesis test for independent groups, and it's a t-test pooled variancy. That means average based on sample sizes. So here's your single earner, double earner. This is what on the average, how much time they spend watching TV here, how much they spend here. And the standard deviation, this information I put into Megastat. And the rest of it, the lower part, is what actually Megastat computed. Now, I just highlighted the important stuff for us. The difference of 61 minus 48, called it 49, is almost 13, right? Or 13. 12.6 to be more exact. So that's the difference between x1 and x2. Okay. And this is actually the difference between the means. The x1 minus x2 is what I called those. These should be different between x bar 1 and x bar 2. Okay, not x1, x2. I just couldn't put the bars on them. So I can, I suppose I could do it here. I can just put, there you go, x bar 1, x bar 2. Now it looks right. Just in Excel, I didn't do that. Okay. And there you go. You see, pooled standard deviation is 16.7 almost. So that's what that is. The standard deviation was 15.5, 18.1. So it's not exactly an average. It's very close to being the average of these two numbers. So this is what the pooled is. And the hypothesized difference, 0 means no difference. And there you go. Here's our p-value. So our p-value is 0.03. Okay. Now remember, when we test hypotheses, if p-value is less than alpha, our significance level, or equal to it, we reject the null hypothesis. So there you go. I have my decision and conclusion here. Since p-value is indeed less than 0.5, we're going to reject the null. This is our decision. Now this part comes the conclusion. This is what our conclusion is. The conclusion is that there is a strong evidence the average time spent watching TV among single earners is indeed greater than that of double earners. Okay, and it's higher by in the tune of almost 13 minutes more, if that's significant for some people. I don't know the practical significance of this. 10-minute more is like, is that going to bring the couples closer together in the long run? Perhaps, I guess. If you spend 10 minutes more together every day for many years, it adds up, doesn't it? Okay. Now, just want to make a note here is that, remember this 0.0313, the p-value is the actual observed significance level. This is not the stated. The 0.5 is what the problem stated. The 0.0313 is what the data suggests. So this is the actual probability of a type 1 error. Because that's what alpha was. Remember, alpha was probability of a type 1 error. So this is the actual probability of a type 1 error. So this means, what that means is that there is a 313 in 10,000. That's what this decimal reads. 313 10,000ths, right? So there's 313 in 10,000 chance that we made a mistake when we said reject the null, and we shouldn't have done that. So the null could still be true. And remember, the null said there is no difference between the mean times. That statement could still be true. But there is 313 in 10,000 chance of that being true. So that's not a likely event. So we feel pretty good about this rejection. Okay. Now, let me go to Megastat and actually do this. Show you how to do this step by step. Okay, so I am now in Megastat. So this, what you need to do, by the way, please make sure that your data is entered this way for 2 sample tests of hypotheses. In this column, you need to do these exactly the way they are. Okay, so type label, mean, deviation, and n sample size. Okay, now in here, this column, I actually have my first group. This is our second sample or second group. Single earners, their average was 61 minutes, deviation 15.5, sample size 15. The double earners, their average was 48.4 minutes, deviation of 18.1 minutes, and the sample size was 12. So please make sure that it looks exactly like this for 2 population means. Next we go to add-ins and Megastat. We're going to go down to hypothesis test. Now in here we have several options. We're going to take a look at compare 2 independent groups. Remember in chapter 10, prior to this chapter, we looked at hypothesis test and confidence interval for 1 population mean, and this one now we're looking at 2. But notice here we have 2 independent groups. There's an option for paired observations. Do not use that. Please use this one. Okay. So we go compare 2 independent groups. Click on that. Now, in here, I'm going to click on summary input. We don't have data input. I don't see the individual viewing times, if you will. I only see summarized data. So click on summary input. Now notice in here, as soon as I click that, let me show you again. Down here in boldface, see something, a sentence is going to appear, a phrase. There you go. Because it's summary input, the expectation is, it reads, for each group, select ranges with label, mean, standard deviation, and sample size. And notice that's exactly what I have here. They have to be in that order. Okay. Now you can call this capital L, A, B, E, L, mean, call it average, standard deviation, sample size. It doesn't matter. This part doesn't matter so much. The order in which you do this matters. So don't put sample size up here, mean down here. They have to appear in this order. So, and there you go. Let's see that? The structure, that's the label, mean, deviation, sample size. So click on group 1. And then left click once and drag. And that outlines the range of cells for group 1. Once you select them, hit enter. Do the same thing for group 2. Let me move over to the, maybe down here. There you go. So I'm going to go group 2. And the same thing, left click once and hold and drag. That outlines the range for group 2, where those information are located. Hit enter. Alright, so at this point, Megastat knows where your data resides. Let's go down here. Our hypothesized difference is going to be 0, but you can hypothesize the difference between the two is 5 minutes between the two groups, 10 minutes, whatever. We're going to go 0. The alternative hypothesis was that, remember, single earner watch more television. So that's going to be mu1 is greater than mu2. If you're doing confidence interval, if you are interested in 95% confidence interval, whatever, see that? You're welcome to put that here, but the question didn't ask for it. But if you did, you can also do confidence interval as well as hypothesis test. You can do both of them here. Now this is important. We're doing a pooled variance. That's based on our assumption because sigma 1 equals sigma 2. So we're going to pool them. And because they're unknown, we need to use the samples. And then we average them according to their sample sizes. So make sure this radio button is selected, and pretty much that's it. We're ready to go. Hit OK. And there you go. This is the output that I had. You see that? Again, this portion of it is what we input. And this other portion right here is what Megastat ran. The difference between single earner minus double earner is 12.6. And again, it all comes down to that p-value, the all-important p-value. And that's how you do this problem. Okay. So let me now go back to my note, and this is what I had exactly in my note. Okay, so here I am back in my note, and there you go. Hopefully now you see how familiar these are. Okay. So we're done with that one problem. So again, we just did an example of two sample pool t-tests for two independent samples, assuming unknown but equal standard deviations. Now let's take a look at the next example. This example is an example of two independent samples t-tests, and this time we're going to assume the deviations are unequal. They're not equal, so we don't have to average them or pool them. So they're unequal. And here's an example. A recent survey compared the cost of adoption through public and private agencies. For a sample of 16 adoptions through a public agency, the mean cost was $21,045 with a deviation of $835, whereas for a sample of 18 adoptions through a private agency, the mean cost was $22,840 with a deviation of $1,545. Wow, that's pretty high. The deviation is almost twice as much as the the public agencies. Maybe the public agencies are governed by government, who knows, as opposed to private. They're not governed by the governor, so they have more flexibility in pricing. They can charge more. And you can see the sample means. The difference in the mean is, it's about $1,800, isn't it? Wow, higher with private agencies. So what we want to decide is whether that difference of almost $1,800 is statistically significant, or is it just random variation, sampling error that just happened. At 0.5 significance level, that's our alpha. Is there a difference in the average cost of adoption? Notice the question reads, is there a difference? It's not siding with which one is higher or lower. But again, judging from the samples, it looks like the price at the private agencies is higher for adoptions. So here's what's given again. this given is what we're going to take with us to StatCrunch. Okay, so first sample size is 16. The second sample size is 18. And we have our X bar 1, X bar 2, S1, S2. You see that? And when I went to, I'll go to Megastat in a moment, but this is given. Now, here again, I'm going to let mu1 be the average cost of adoption through first public agencies. And the second one is private. There you go. I bold-faced them. So that's what those are. Now remember, the null, we always take them to be equal. The null says there is no difference between anything. So the cost of adoption is the same. Doesn't matter whether you go to public or private agencies. That's what the null says. We want to know if there is a difference. The researcher want to know if there is a difference. The change in status quo. So I ran this in Megastat. And this is the kind of output you expect to see. It's very much like the one above it, right? The case where we had our assumption was that they are unknown but equal. That's the population deviation, that is. So here is public, and this is for private agencies, sample size, and so on. Again, I input this information, and you'll see it in a moment. The rest of it was done by Megastat. Look at the difference, public versus private. Almost $1,800, you see that? A negative difference here means private is higher, because we go X bar 1 minus X bar 2. So a negative difference means higher cost on average in the private agency. And wow, look at that p-value. This is definitely beyond reasonable doubt. It is more than clear and convincing evidence. This is 0.0002. That's 2 in 10,000. 2 in 10,000 chance that we're making a mistake when we say reject the null. This is the actual probability of a type 1 error from this samples, these two samples. So here's my decision. Because p-value is less than 0.05, we definitely reject this null, and there's very strong evidence. The average cost of adoption in public-private agencies are not the same. And again, it looks like they're higher in the tune of $1,800 at private agencies. So how are we going to do this in in Megastat, right? So let's go to Megastat. Okay, so I'm back in Megastat now. Let me go to sheet 1. Okay, so we just used this data for previous example. Now we are over here. So this is how, again, you want to input your results. Again, this labels don't matter. You can do all caps. You can call mean average. You can call this standard deviation, full verbiage. What's important is the order of these. It has to be labeled mean deviation n. And there you go. This is for my first group and the second sample. Public agency, that's the average deviation sample size. Okay, so we're going to go to add-ins, Megastat, and we're going to go down to hypothesis test, compare two independent groups, right? We're still doing two independent groups. Click on that. Now, summary input, we're going to keep that. Group 1, actually now this is a different exercise, so highlight and choose them. Group 2, let's select these. Remember, left click, hold and drag. The hypothesized difference, keep it at 0. And this time we just want to know if there is a difference. So I'm going to change the alternative to not equal to. Now this time look at our choice. Remember, we're not going to pool this time. We're going to go unequal variances. So we're just going to do a t-test. Two group t-test. And that's it. Hit OK. And we're going to see, there you go, here's the output. Very similar to the one directly above it. You see that? These two, the format, the structure is the same. And there you have it. Look at the p-value that I got. The difference is $1,800. And again, We already talked about it. I just want to show you how to do this step by step. Okay, so I'm going to go back to my note again. Okay, so I'm back in my note and we're done with this example. So we're done with the two cases for independent samples. Now we're going to the last case, the last scenario. In comparing two means, the change is in our design. This time we're going to assume we have dependent samples. So what do we mean by dependent samples? And this is what we want to do. We want to do two sample tests of hypotheses for these dependent samples. Okay. We still want to compare two population means, but what we've changed is in fact the structure of our experimental design. Okay, so these two samples are no longer independent. So what are dependent or paired samples? I'll show you several examples in a minute, but usually dependent or paired samples, we use them interchangeably. These are created through either matching of experimental units, or you have some kind of a before and after effect. Okay, so again, you have either you match two things, a pair of subjects together, or you create a before and after effect on the same experimental units. Okay, now this before and after effect, you actually, some people say you apply two treatments to same experimental units. Again, I'll show you several examples. This is going to become easy in a minute. Easier. So, in this case, you have one set of experimental units or individuals that are matched. Okay. Let's take a look at our examples. So, in this example, we're going to see here. Let's say we want to see how effective a diet is. So, what are we going to do? We're going to measure the weights of individuals before they go on the diet and after they go on a particular diet, maybe 2 weeks later, 3 weeks later, whatever that time interval is. But you see how in this example, this is your before and after example. Notice we have the same individual. You only have one person, like myself. They can measure my weight before on the diet and then my weight after I go on the diet. So I don't represent two different samples. I'm really one experimental units, and they're applying two different treatments to me. Okay, the treatment here would be the weight before, and the treatment would be the weight after. Those are the two treatments. Okay, let's look at another example. Again, this is another before-after effect. Let's say we want to look at, we're going to measure the carbon monoxide emissions on a group of automobiles before we increase the oxygen in the fuel tanks and after. So I'm going to take my car and I'm just going to put regular gasoline in it. Okay, just regular unleaded. And then I'm going to measure the carbon monoxide emissions. And then I'm going to add some kind of a oxygen supplement, okay, in the fuel tank. Some kind of gas treatment in the fuel tank, and then they're going to measure the carbon monoxide emission afterwards. So you see, it's the same car. It's my car before and after the gas treatment was applied. Now, what are examples of matched pair, which creates dependent samples? Let's say we're interested in comparing social attitudes of twins. Now notice twins, these are actually two subjects. Right, two different people, but because of the similarity in their physiological structure, it makes sense to pair twins together. So we're going to have one child that stays home with a family and the other lives with a minority family for a few weeks. Then we compare the scores on a questionnaire, see how we match them. This is actually where we have two different experimental units, but we match them, pair them together. Here's another example of matched pair. Let's say I want to compare ages of a married couple. Okay, so let's say it will be Mr. and Mrs. Johnson. You compare their ages. You're going to group them together. It makes sense. So together they form a single unit, experimental unit. And another matched pair example. Let's say we want to compare the rest pulse and run pulse on the same subject. So they're going to measure my rest pulse, and then I'm going to run around the block, come back, measure my run pulse. So it's same subject. You have two different measurements on the same subject. Another example. Let's say we're going to answer this one question. Do younger women prefer older men or vice versa? This would be another example of matched pair, right? So this would be where, for instance, you look at again, you go back to the ages of married couple in order to answer this question. So this is really an overlap of these two. But the design structure here is going to be a paired experiment. So the question might be now, why do we want to pair these together? I guess it makes sense based on the examples I have, why we want to pair them. So for example, let's say an insurance company is suspicious of high estimates from one body shop. So let's say what the company does is that it will send, one way to do this is to, let's say, take 10 cars that were in accidents to body shop A, and then 10 different cars with similar accidents. Keyword is similar. Like, how do you know they're exactly similar or identical accidents to the second body shop? And then we're going to compare the average estimates. Well, that doesn't sound right, correct? Because we got 10 different cars going to body shop A, 10 different cars with similar accidents to body shop B. We could actually remove the effect of automobiles, right, between the groups by taking the same car now and getting two estimates on it, right? So here pairing makes sense. So what pairing does in effect, it removes the variability between the two groups, right? So that's what I have here. So by doing so, it results in a smaller sampling error. And if you have a smaller sampling error, we are more likely to detect differences due to the treatments. Okay. Now, conceptually, how is this going to work? So this is our design. We're going to assume we're sampling from two normal population. This would do the before after. Okay. And remember, with before and after, you have the same experimental unit. You don't have matched. But it works in case of match also. So this would be like the distribution on the left would be the weight before diet. The one on the right would be the weight after diet. These are individuals. So we have millions of individuals here. And their weights, same millions of individuals are in here now. These are the weights before, the weights after. So let's say my weight is here before, and then my weight after is here, hypothetically. Okay, so we want to compare the averages. Remember, keep your eyes on these. You want to compare the average weight before and the average weight after. In the case of a diet, if the average weight after is lower, that means the diet is effective. It works on the average person. Okay, and then what do? We're going to pair them together now, right? Remember, it's the same subject, so we get a sample of size n pairs. Okay, so that's what it is. The sample size is n in this case. You just get one pair of sample. So again, it's going to be my weight before and after, your weight before and after. So we get one sample. But the theory says you take repeated sample of the same size. So we're going to pair these together. And with this pairing, we're going to form a new variable, d, which looks at individual differences here. Mu d is the center, is the average difference. And of course, sigma, this normal distribution here. This has its own standard deviation, right in here. That's sigma d. And mu d, of course, is unknown and needs to be estimated. Now, if we can do that, that would be great. Now, what we're going to do is, because these are individual differences, millions of individual differences are here, mine is in here also somewhere. So we're going to take repeated samples, again, of the same size n that we had here. And actually, there we go, from here to here is where we take sample of size n. Okay. Up here, we just pair them. We don't take a sample here yet, right up there. Remember, because we're having every member of the population here is going to have itself a score here. So we don't sample here. Sampling takes place right down here, from this to this step. So we want to estimate the average difference. We're going to do that through a sample. Now the sampling distribution is going to be normal with its mean and deviation sigma. And this is exactly what central limit theorem was. Remember, and what we have done in effect, let me summarize this. We take two groups and we actually reduce it down to one group through their differences in scores. And in effect, we have one sample here at this point. We have one sample. And once we have this one sample, we do a one sample t-test. And these are the parameters of this distribution. Mu of d bar is exactly the same as the mean. This is unknown and we want to estimate. And we use this distribution because its standard deviation is less than the one above. Okay. Let's take a look at an example, and we're going to again run this through Megastat. So this is an example of before and after, kind of. So with before and after, treatments are applied to the same experimental units. Remember, same. So we don't have like twins. We don't have husband and wives. Like it's one person, you have a before and after effect. So in this exercise, and don't worry about the number here, so that will confuse you. There. That's really not the problem number. Okay, so in this exercise, we're going to look at the corneal thickness. Okay, so the question reads, glaucoma is the leading cause of blindness in the US. Okay, so this researcher measures the corneal thickness of 8 patients. Notice how small the sample is, by the way. With small samples, it's really difficult to test hypotheses or do anything. The results are not really as good as they should be. So as much as possible, we would like to have large samples. But that's okay. So 8 is what they have. 8 patients who had glaucoma in one eye but not in the other. Notice you only have 8 patients, but you're measuring 2 different scores on that same experimental unit. A patient here is our experimental unit. Okay. So we're looking at these patients that had glaucoma in one eye, not the other. Now notice how this design was done correctly. Instead of looking at, for example, 8 people that have glaucoma in one eye, and 8 different in these glaucoma in one eye, and 8 different people with normal eyes and comparing their corneal thickness, that would be inaccurate. This is the correct design for this exercise or this research. And there's actual citation. The following data are the data on corneal thickness in microns. A micron is like 1 × 10⁻⁶ power. Micron, inches. So that's 484 microns. That's 484 × 10⁻⁶. So it's like 0.000. That's 3 zeros, and then 484 inches. A very precise measurement, huh? So there we have it. Question reads, at 10% significance level, do the data provide evidence to conclude that mean corneal thickness is greater in normal eyes than in eyes with glaucoma? Now, if I look at this data, by the way, for example, look at this, 478, 478. So if the difference D is 0, means there is no difference. For the normal eye, if the corneal is thinner in the normal eye, 484, in this case thicker in the eye with glaucoma, then this is like the mu1 minus mu2, or x1 minus x2, 484 minus 488. A negative difference is what I'm trying to clarify here. A negative difference means the corneal thickness in the normal eye is thinner, not thicker. Now 492 thicker than 480. So if I take 492 minus 480, that difference is 12. A positive difference means thicker corneal thickness with the normal eye. Okay, so I'm going to let mu1 be the average corneal thickness in the normal eye, mu2 the average corneal thickness in the eye with glaucoma. The null says the difference is 0. There is no difference between corneal thickness between normal and eyes with glaucoma. In other words, null says glaucoma is not a degenerative disease. Whereas the researcher here, the question says, can we conclude that thickness is greater? Remember, if it's greater, look at this last pair. If it's greater, that means the difference must be positive, right? This is greater for the normal eye and smaller in the eye with glaucoma. So a positive difference greater than 0 means how we set this up. And here's using Megastat. Again, I'll show you how I ran this in a moment. But this is the hypothesis test. Paired observations, what we have. So this is the average corneal thickness for the normal eye. This is for eye with glaucoma. Look at this. On average, is positive 4, means thicker. So the normal eye is thicker by 4 microns. That's 4 times 10 to negative 6 power. Again, that may not be a big deal. That could have happened by just chance, sheer chance. Okay. So if I go down here, look at the p-value. And the p-value is 0.1637. 16% p-value. So that means the difference of 4 micron is nothing to write home about or get excited over. It's just sampling variation. Now another view of this p-value, 0.1637, by the way. Here's another take on this number. If you and I were to conduct this experiment, like this researcher has, we go out and get a sample of size 8 patients from where he got his from. And we conduct this experiment. We do it all over again. There is a 16%, better than 16% chance that we get the exact same results they got. So if it's, and this is probable, isn't it? 16% actually is probable. So if it's something that's probable, then it's nothing special, right? So we haven't seen an extraordinary event. That's why small p-values are good. With small p-values, like something in the order of 1 in 1,000. If we get a p-value, let's say 0.001 means 1 in 1,000, that means you have observed an unlikely event if the null is true. So, and then we go about rejection at that point. But with this one, we're not going to reject the null. This data is not so special. So it could be replicated, and we could expect to get the same results even when the null is true. The null said there is no difference. So when there's no difference, 16% of the times you get the same results this researcher got. So since p-value is not less than significance level of 10%, we fail to reject the null hypothesis. And we conclude there is no difference in the average corneal thickness between the normal eye and the eye with glaucoma. Okay, so let's now go and actually do this in Excel using Megastat. Okay, I'm now in Excel, so let me actually go to or data. Okay, we just did these two examples. There you go. This is the one. Ignore this one, please, for now. Don't look at it. So we're looking at this one. This will be our next example. So here's the example for the glaucoma, the corneal thickness, that is. This one. So I created two columns, normal eye and eye with glaucoma, and I actually input the scores here. Right, so I have 8 pairs of data. So to do a pair t-test, you go to add-ins, make a stat, and we're going to go to hypothesis test and look at this entry. You see that? Paired observations. We're going to click on that. And this is what pops up. I'm going to go summary input. Oops. Use mean versus. Okay. Let me see. Let me X out. I did something wrong. Let me go back. Add-ins. Make a stat. And we're going to do hypothesis test paired observations. And oh, I see. I don't have summary input. That's why I clicked on the summary input. See, this is data input. You see, if you can actually see the raw data, the actual scores, you have data input. You don't have summary. Summary is if they give you the mean, the deviation, and the sample size. So we have data input. And then group 1. Make sure you select the label and select that range. Hit enter. And then you go to group 2. Select this range. Hit enter. And let's see here. Hypothesize. The difference 0 means there is no difference between the two, the corneal thickness to the two eyes. And the alternative here, remember we want to know if the normal eye was thicker, right? So mu d was greater than. There. A greater average means thicker corneal thickness. And we're going to do a t-test here, and that's it. That's all you need here. Again, if you want to do a confidence interval, you can click it, but the problem doesn't ask for it. Don't worry about confidence interval here. Now, hit OK, and there you go. So this is how I got those numbers. Remember 0.1637? That's what this one is. Okay. So just wanted to show you again step by step how to do this in Megastat. So let me go back to my note now. Okay, I'm back in my note, and let me go down to our next example. Okay, so this is the second example of paired experiments or dependent samples. So the first one was a before and after kind. This is an example of a matched pair. So this is in your book also. The question, the null alternative are given. The average difference is 0 versus the alternative. The average difference is different from 0. Means there is a difference between the two scores on average. Now what are the scores in this one? The following paired observation show the number of traffic citations given for speeding by two officers, Officer Daunt and Officer Meredith of the South Carolina Highway Patrol for the last 5 months. Okay, so there we have the data. At 5% significance level, is there a difference in mean number of citations given by the two officers? Okay, so notice here now, for example, we're going to look at in May. We're going to compare them in May. We're going to compare the two officers' citation record in June. We're going to pair them by month in July, August. So the months serve as a blocking factor in this case, right? And we're going to answer these questions. What is the p-value? Is the null hypothesis rejected? And what's the conclusion? Pretty much the way we've been doing it. So we're just going to run megastat, right? Now, I'll show you the details, but here's actually the run. The hypothesized value was 0. Now, the average number of citations Officer Daunt has given is 24.4 versus Officer Meredith on average almost 20. The difference is about 4 citations per month. 4.6 to be exact. Almost called it 5. The question is that statistically significant? And you can see, again, the first officer is issuing more citations. Okay. And check out the p-value. The p-value is 0.0025. So that means there's 25 in 10,000 chance. We're going to reject this definitely. We have clear, convincing evidence. But there's 25 in 10,000 chance that we make a mistake when we say reject this null, and the means could still be the same in the long run. So the answer to part A, to p-values here from the output. Now remember, alpha was 0.5, right? Right up here. See, 0.5 significance level, that's your alpha. The stated probability of a type 1 error. Since p-value is less than 0.5, 0.025 is much less than that. We're going to reject the null, and we're going to conclude that there is no difference. Actually, we reject the null. The null said there is no difference. Yeah, null always says that. So there is a difference. Let me fix that. There you go. There is a difference in the average number of citations given by the 2 officers. Okay. And there you have it. So we are done with this chapter. Again, in this chapter, we looked at 2 sample tests of hypotheses. We look at the case where we have 2 independent samples, and we look at a case where we had 2 dependent samples. Okay, and with that, we're done again with chapter 11.